Welcome back. So in this very particular video, we will be discussing the next 5 questions of first chapter of 12th class NCERT chemistry back exercise. The chapter is the solid state. So I will be taking up question number 16 to question number 20 in this particular video. So let us now move into it and see what we need to find in question number 16. All right. So let's see what is the statement for it. The statement is, analysis shows that nickel oxide has the formula Ni 0.98 O 1.00. What fractions of nickel exist as Ni2 positive and Ni3 positive ions? So we need to find out the fraction of Ni2 positive and the fraction of Ni3 positive ions which are present in this particular nickel oxide crystal. Okay. Now, if you see, this is non-stoichiometric. Okay. If we say that all the nickel present in this oxide is nickel 2 positive, what will happen? It will not be able to neutralize the complete negative charge of oxygen because the amount of oxygen is more than that of nickel. But always as a whole, the crystal is electrically neutral. To make it electrically neutral and to compensate the positive charge, nickel 3 positive will be present at certain places. And now we need to just find out what will be the fraction of nickel 3 positive and nickel 2 positive. All right. So let us now first assume that let fraction of Ni plus 2, it is equal to x, and therefore fraction of Ni plus 3 positive, it will be equal to 0.98 minus x, or the amount. We can just write here amount. Amount of nickel 3 positive is this, and amount of nickel 2 positive is this one. Now, we can just find out what will be the total positive charge and what will be the total negative charge. Okay. Positive charge due to Ni2 positive is equal to 2 into x, because 2 positive is the charge and total amount is x, so 2 into x. Negative charge or the positive charge due to Ni plus 3, that is 3 positive, it will be equal to 3 multiplied by 0.98 minus x. Now, the total negative charge due to O2 negative, because oxide ions are there, it will be equal to minus 2. So the total negative charge is minus 2. Now the total charge on the crystal, it is equal to 0. So what we can do is we can add the positive and the negative charge and put it equal to 0. So 2x plus 3 into 0.98 minus x minus 2 is equal to 0. So 2x plus, let us just quickly calculate what is 3 into 0.98. So it is coming out to be equal to 2.94 minus 3x minus 2 equal to 0. Now what you can do is combine the terms with x and without x. Okay. So 2x minus 3x, it is equal to minus 2.94 plus 2. So minus x will be equal to 0.94. X will be minus 0.94. X will be equal to 0.94. So this is the fraction of Ni2 positive ions. What will be the fraction of Ni3 positive ions? Total fraction is always equal to 1. Okay. So the fraction of Ni3 positive will be equal to, it will come out to be equal to 1 minus 0.94. So 0.06. So this will be the fraction of Ni3 positive ions. So it will be, if we need to find out the percentage, 94% will be Ni2 positive and 6% will be Ni3 positive ions. Hope this is clear to you. And let us now move into the next question, that is question number 17. The question number 1.17 is, what is a semiconductor? So there is a conductor, there is an insulator, and in between there is a semiconductor. So conductor, insulator, in between there is a semiconductor. So conductor is a substance which allows the flow of electricity through it. Okay. Insulator is the substance which does not allow the flow of electricity through it, and semiconductor is, it will allow the flow of electricity through it, but not as much as the conductor, and it will have the conductivity more than that of insulator. So insulator, it does not allow it at all. Conductor allows it to a large extent, and in between is the semiconductor. So the value for conductivity in case of semiconductor is 10 raised to the power minus 6 to 10 raised to the power 4 per ohm per meter. Now in this case, in case of semiconductor, what the case is, there is a conduction band and there is a valence band. This is the conduction band. Conduction band. There is a valence band. And the energy difference between these two is very small. Very small energy difference. So because of small energy difference, the electrons, they can jump from the conduction band to the valence band, and they allow the flow of electricity. Okay. Now let us move into the second part of this question. Describe two main types of semiconductors. So two main types of semiconductors are N-type semiconductor and P-type semiconductors. N-type semiconductors and P-type semiconductors. Okay. And then we need to contrast their conduction mechanism. Contrast their conduction mechanism, how they conduct electricity. Let us first consider the N-type semiconductor. Now, from where we are using this prefix N, it is negative type. Okay. What we do is we take the element of the 14th group. You can just consider silicon or germanium. You can consider silicon or germanium, and you can add an impurity from the 15th group to the 14th group element. Okay, so the 15th group is the nitrogen group. Nitrogen, phosphorus, arsenic, I'm so sorry. Nitrogen, phosphorus, arsenic, antimony, bismuth. Phosphorus and arsenic are used for doping. What is the meaning of doping? Doping is addition of impurity. Addition of impurity is doping. So we are taking group 14 element. Okay, so I'm supposed taking silicon. Now number of valence electrons is 4. 4 valence electrons. Now when silicon will be doped with phosphorus, what will happen? Phosphorus or arsenic, you can take any. So suppose these are the silicon atoms, and here we have put one arsenic. These are all silicon. Okay. Now in arsenic, what is the number of valence electrons? 5. Number of valence electrons is 5 because it is from the group 15 element. It is having 5 valence electrons. Now what will happen? All the silicon atoms, they are forming 4 bonds with other silicon atoms. So you can just draw it a bit to the center. Okay, so all the silicon atoms, they are forming bonds, 4 bonds with other silicon atoms. Now when we will be doping it with arsenic, what will happen? Arsenic will be able to form 4 bonds and 1 electron will remain free because it is having 5 valence electrons. 4 are available for bonding with silicon, and but 5th electron is not there with silicon, so it will not be able to bond with silicon through its 5th electron. So that electron is going to be free. Okay, now this free electron, it can move freely in the semiconductor, in the lattice. It can move freely in the the lattice, that is, it is delocalized. Delocalized. It is not fixed at one point, but it is delocalized. That is, it keeps on moving from one to the other point. So when there is flow of electrons, there is flow of electric current. Now, why do we call it as N-type semiconductor? Because there is an extra electron which is negatively charged. So that is why we call it as N-type semiconductor. Okay. Now let us move into the P-type semiconductor. So if suppose we have the group 14 element, again, you can take silicon, you can take germanium, any you can take. So these are the atoms of the group 14 element, whatever you have considered. And one has been replaced with boron, suppose. That is the group 13 element. Now, what is the number of valence electrons in boron? It is 3. But in case of 14 group elements, it is 4. So they will be forming 4 bonds with the other similar atoms. But boron will not be able to form 4 bonds. It will be able to form 3 bonds. Suppose this is 1 electron of boron, this is another electron of boron, this is another electron of boron. So they are forming bond with 3 other silicon atoms. Okay. Now, what will happen? It will appear here, boron is not having electron, but this silicon is having this electron because it is having 4 valence electrons. Now, it will appear as if there is an empty space which has been created because of non-availability of electron. That empty space is known as electron vacancy or hole. Electron vacancy or hole. Now, what will happen? From the neighboring atoms, the electrons can keep jumping into this hole, and it will appear as if the hole is moving. This means that the conduction of electricity is because of the presence of electron vacancy. If electron is considered negative, electron vacancy will be considered positive. Electron vacancy will be considered positive. So that is why we call it as P-type semiconductor. Hope this is clear to you. Now let us move into the next question. Let's see what is the question number. Question number 18, 1.18. So it says non-stoichiometric cuprous oxide. Okay, cuprous oxide is there and it is non-stoichiometric. It can be prepared in laboratory. In this oxide, copper to oxygen ratio, Cu is to O, is less than 2:1. Otherwise, it should be equal to 2:1, but it is actually less than 2:1. Can you account for the fact that this substance is a P-type semiconductor? Can you account for the fact that this substance is a P-type semiconductor? Now, if this ratio is less, this means copper 2 positive is missing from some places. It will be missing from some places. Now, to compensate that charge of copper 2 positive, copper 1 positive can take that space. So after 1, if we consider there is only 1 copper 2 positive missing, we need 2 copper 1 positives to compensate that 2 positive charge. So suppose I'm just drawing only the coppers. Okay, so we can just take it, and I'm just saying that copper 2 positive is missing from this place. And copper 1 positive is taking up this place. All other are copper 2 positives. All these are copper 2 positives. Now this copper 1 positive is taking one place, but another copper 1 positive will also be required, which will be taking some interstitial space. Because other site is not available. So it will take up some interstitial space. Now what will happen? Because this is in the interstitial space, it can move. So when it will move, it will lead to the conduction of electricity. Now, because the conduction of electricity will be due to the positive charge, so it can be considered as the P-type semiconductor. Because the conduction of electricity is going to be due to the positive charge. All right. Now let us move into the next question. Question number 19. Let's see what is the statement for it. I'm just clearing my screen off. Okay. Ferric oxide crystallizes in a hexagonal close-packed array of oxide ions. Okay, 1.19 question is there. Ferric oxide, it crystallizes in hexagonal close-packed array of oxide ions with 2 out of every 3 octahedral holes occupied by ferric ions. Derive the formula of ferric oxide. We need to derive the formula of ferric oxide. Now, if we consider hexagonal close packing, it will be like this. This is the layer A. Okay. Here also there is oxide, and 3 oxides are inside the space of the hexagon. Actually, these are all touching each other. Just to make it simple, we do not show them touching. Okay. Below this also, the second end of the hexagon, these are all oxide ions. Okay, so you can just connect these dotted lines. To the dotted lines you can connect so that you can show the hexagonal shape. Okay. Okay, now this is the hexagonal shape, HCP, hexagonal close packing. All these that have been shown in this figure, they are all oxide ions because they are taking the lattice sites. First of all, we need to find out how many oxide ions will be there per unit cell. So oxide ions per unit cell. First of all, consider the corners, all these corners. So in hexagon, one corner will be shared by 6 other hexagons. So how many corners are there? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 12 multiplied by 1 upon 6 equal to 2. Okay. Now 3 oxides are lying inside the hexagon. They are not shared by any other hexagon. So here we can say 3 oxide ions. Now the ones which are present at the end centers. Now one end center will be shared by 2 hexagons. Okay. So 1 upon 2 into 2 equal to 1. So the number of oxide ions per unit cell is equal to 2 plus 3 plus 1 equal to 6. Okay. Now we have been given that 2/3 of the octahedral holes are occupied by ferric ions. First of all, we need to know what is the number of octahedral ions. Number of octahedral ions is equal to the number of lattice sites. So number of octahedral ions, voids, it is equal to 6. Okay. Now out of 6, 2/3 have been occupied. So number of Fe ions per unit cell is equal to 2 by 3 into 6 equal to 4. This means Fe is to oxygen is equal to 4 is to 6, or we can say 2 is to 3. So it is Fe2O3. So this is the formula for ferric oxide. Hope this is clear to you. Now let us move into the next question. Classify each of the following as being either a p-type or n-type semiconductor. So we have been given 2 semiconductors. We just need to tell whether they will be the n-type semiconductor or p-type semiconductor. Germanium doped with indium. Now indium is a group 13 element. So this means it will be having only 3 electrons in the valence shell. This is having 4 electrons in the valence shell. So 1 electron will be short, so there will be a hole. So whenever there is a formation of hole and the electricity is conducted due to the presence of a hole, the semiconductor is p-type semiconductor. So it is p-type semiconductor. The second part to this question is you can write the complete explanation of this one because we have already done the similar question in this very particular video. Okay, that was the question number 18th or no, 17th. It is 17th question number. Okay, you can refer to that. B is silicon doped with boron. Okay. Now again, boron is also group 13 element. It will be having 3 valence electrons. This will be having 4 valence electrons. Again, there will be formation of a hole. Conduction will be due to the presence of a hole. So again, it will be considered as a p-type semiconductor. So hope this is clear to you. And for this video, this is sufficient. Do it, thoroughly understand the questions, and then we will be moving into the next 5 questions. So see you in the next video, and do like and share this video with your friends. Subscribe to the channel and press the bell icon also. Thank you very much.